Today I'm going to present you the measurement calculus. It's a formal framework, a computation model for quantum computation that is a bit different from the usual circuit model, where you have a quantum state and evolve it with unitaries, then you do the measurements. Here, uh, we put more in this formalism, we put more emphasis on the measurements itself, and also it has some other benefits like separating the entanglement part from the uh, entanglement part from the start and do the evolution afterwards. So let me start by introducing some comments that we were going to use in the formalism. First of all, there's a preparation comment that we denote with ni, which prepares ith qubit with the plus state. Here we are focusing with a setup where we have finite set of qubits, and this command says that we are preparing the ith one with the plus state. And the second one is the entanglement command. We denote it by EIG. That applies basically CZ on those qubits, ith and jth qubits. Then the main command that we are going to build the theory on is the measurement command. We denote it by MI alpha, which measures ith qubits in the following basis. We denote it by plus alpha and minus alpha, and where they are defined as plus alpha is the 0 plus AI alpha minus, 1, and the minus alpha is the similar to the plus and minuses without alphas, that we have the minus sign in here. So we have measurements where alpha is a real value, so we have different measurements, like set of measurements, family of measurements that we are going to use. And also it is important that in this framework we are focusing on the destructive measurements. So after we measure, we just trace out the qubit and do not do anything with that qubit. So it is important to note that. So the dimension of the Hilbert space that we are working on reduces after we do the measurement. And also we denote the outcome of the measurement by Si, which is an element of Z mod 2. And we say that if Si is equal to 0, then we collapsed onto the ith qubit on the plus alpha state. And if, okay, let me write it this way. If it is 1, we say that it's collapsed onto the minus alpha state. Also, sometimes we are interested in like the combination of measurement outcomes, because we are going to work on the adaptive operations that depend on the measurement outcomes. So we also use a term called signals, which are basically sums of measurement outcomes in some subset, but the sum is evaluated on Z mod 2. So we also use those because some commands may depend on more than one measurement outcome. And the last one is the corrections. So they are just Pauli gates on Xi, just the two of those, not the Z part, but those are the combinations. So you also have the Z Y part. Those are the Pauli X and Pauli Z gates on ith qubit. But this is not the all comments, because if we just restrict it to this case, we cannot achieve universality. We need to have the adaptive versions of measurements and corrections. So we denote them as such for S and T in Z mod 2. Those are the measurement outcomes or signals in general. So XIS just applies X to ith qubit if S is 1, but does nothing if S is 0, and similarly for the Z case. And for the measurement, we have a bit of different notation that we denote it by mi alpha, but we have T and S on both sides. This may seem arbitrary, but I will explain it after I write it. -1 over S times alpha plus T pi. So they arise from the conjugations of measurements by X and Z. So we have the following relations. Xi, mi alpha xi is equal to mi minus alpha. We can see that from the definition of those bases, because X just swaps 0 and 1. So we'll get the opposite alpha, because we are the states are equivalent up to overall phase. If we change 0 and 1, we will get the minus alpha version. And similarly, if we conjugate with Z, we will get the mi alpha plus pi. So those are so this is the minus part, this is the plus pi part. Those are the dependencies that we have on measurements. And furthermore, as we mentioned, we are interested in the destructive measurements. So if we restrict it to the case of destructive measurements, like in our framework, we can just delete those parts because they are done after the measurement. So they have no use for us. So we can, yeah, it is not an equality by formal means, but we can just write them as such by deleting the last operation, since we are um, concerned with the destructive case. And we will later show that those are justified because they will realize the uh, same operation if we just delete it, because we are not interested in the ith qubit after we measure it. But we also need to define the measurement patterns in a more formal way. We are going to do it as such. So pattern consists of the following data. First, we have a finite set of qubits that we denoted with V, and we call it the configuration space. And also we have a Hilbert space, HV, attached to it, that we define by E in V C square. So it's the basic qubit space with that many qubits. And also we have the inputs and outputs, which are the subsets of our general operation space, configuration space V, and they also have their associated Hilbert spaces that we denote with HI and HO. Those we denote with inputs, and this is the outputs. Uh, but there are also like in general we don't have this one because they may be different. So there are also qubits that are not an input or output qubits, and this is not true. So lastly, we have a finite sequence of comments that we denote with an to a1. In the usual way, we are reading from the right from left as we do to unitaries. So those comments apply to the qubits in V. But uh, our comments are, like as you can see here, makes more sense if we put some restrictions on them. For example, it is not meaningful to measure something that we haven't prepared or doesn't come from the input yet. So we also have some constraints that just make sense to have. So I will just write it. For example, the first one, we denote the whole set of constraints by D, but there will be 4 of them, and D0 will be the uh, restriction says no comment depends on an outcome not yet measured. So I can write D0. So I think it just makes sense because otherwise we cannot do anything because we don't have the measurement yet. So so the other one is the since we assumed the destructive measurements, we also have the restrictions of no comment acts on a already measured qubit. Measured qubits. And the third one is no comment acts on a qubit not yet prepared unless sorry okay unless it is an input qubit. Uh, like we have the input qubits and we have the others are prepared in the plus state. So if something just comes before the preparation, we don't know the state, so we cannot do the operation. So we have those restrictions. And lastly, a qubit is measured if and only if it is not in O. So basically, when we start with V, we measure the all qubits except the output ones. So we get the output state by leaving the remaining ones. Okay, we denote the pattern, let's say the P, as V, I, O, and the comments AN to A1 as a tuple. So I can further demonstrate how we run those patterns. So first of all, I will make a simplification assumption that all all preparation commands are done before the other ones. So I just you can think that like I moved all the preparation command to the beginning. So our pattern takes an input state psi in the input Hilbert space. this is the first step. Then it adds the tensors of the plus state as the preparation does to get a state in the HV Hilbert space. That's an expanded Hilbert space. We are expanding the uh, input space by attaching plus states next to it. Then we start applying comments. Uh, it is straightforward if it is not a measurement. If let's say, okay, I will do not A1. So since I made the assumption of preparation comments comes first, those remaining ones here are one of the entanglement, measurement, or correction ones. So I will just split it into two cases. If AI is not a measurement, it is easy because uh, it is now entanglement or correction. Both of them are unitary, so we just find the uh, sorry, I can write it this way for writing it recursively. Apply it to psi I. Those are the steps. You can think them as the steps to get psi plus 1 equals AI psi I. So this can be thought as the psi 0. Then we are applying the non-measurement comments as unitaries to get the new ones. But it is a bit complicated. It is a bit more complicated, not much, not too much. But if AI is a measurement, then we have branching because measurement can have uh, either outcome. So there's a randomness in it. So we will have two options here. Si equals 0 and Si equals 1. But those are just states after we collapse those. So we define them as state after destructive measurement collapses to uh, collapses jade qubit, jade qubit, and trace out. And similarly, we have the exact same version here. So I can just copy and paste it here. Basically, we have two options for the measurements. And one important thing is we are storing the outcomes. Oh, sorry, it's J. Sorry, because we are, though I want it to be a different index than the index on the index on the command sequence. So we store the measurement outcome Sj, and also we remove J from V, because since we are working with the distracting measurements, it is no use to us after we measure it. So, and also the associated Hilbert space reduces its dimension by 2. Also, there's a those we also assume that.
Oh, I think you mean the dimension is divided by 2.
Oh yeah. Okay. Yes. Yes. Sorry. Okay. Also, in the usual quantum computation, we assume that we normalize the states after we make measurements. But here we say that we assume that the states are left unnormalized after measurements. It is important because it gives a way to find the probability of getting this branch sequence. For example, if you have like, let's say S1 is here, and then you have S2, so measurements, branches, all those things. Then you have this states, say psi, phi 0, phi 1, phi 2, etc. So the probability that we will find phi 0 is just the norm of it. So since we are doing not normalizing after the measurements, it becomes useful in a sense that we are just have a way to find the probabilities of reaching those states after the measurements. So we define it like this. And also, we can see it as in a picture. Okay. We get a state in HI. Then we prepare it to get a state with pluses added in HV. Then we do the comments in the pattern to reach the state. Oh, sorry, I'm using the bracket notation, so we are reaching the psi n+1 state, and here it is the output state, and this is the collection of measurement outcomes. So this is a vector, so you can think it as such, measurement outcomes. So it's in the HO times Z over V over O. So after we do all the pattern, we are left with the output state along with its measurement outcomes in the comments that we apply.
I have a question.
Sure.
So you're measuring everything outside of O, I think.
Yeah. Okay.
S hat is, but I think it should be Z mod 2, right? Not Z. I guess you're
Yeah. Okay.
finding outcomes, right?
It's a mistake of mine. Sorry. It's Z mod 2.
Oh, okay.
One of the constraints that we had here, like D3, is we measure all the qubits that are not in the output ones, that are not the output ones.
Yeah, but the other question here, so when you explain this, V is not equal to I union O necessarily, right? There might be more qubits outside those two sets. I think you can also have a non-trivial intersection of I and O, right? That's also
Yeah, it is possible. They're defining it in a flexible way. They mention in the paper that there is no use of restricting that I and O are disjoint sets. Also, they define it in a way that they are not the subsets of it, but there's an inclusion from I to V and O to V. But I just made it a bit simple.
Okay, so yeah, maybe when you give an example, it might be helpful. But I don't know if maybe there are some questions at this point. It might be a good place to maybe get some questions or comments.
Yeah, of course. Yeah, if there's anything that seems confusing, I can further explain this. Do you have any questions?
Okay, I guess it seems I'm the only person who was confused. Okay.
Okay, now those branching processes very important for us So actually, we can see it from directly that each branch has unique uh, S vector from the in the as a measurement outcomes, because the branches are defined as the like it comes after the measurement. So you have 2 over m branches if you have m measurements. It may be the case that the output states of 2 different branches may be the same, but uh, still they are the different branches because they have different measurement outcomes. So uh, so we denote the linear map uh, from the input Hilbert space to the output Hilbert space for each branch S as AS. This this is how they use as the notation. It's maybe a bit confusing because they use also the commands for the A's, but it makes sense because the AS is just combination of those comments. It can be justified as such. And also, this gives a definition that we can define the realization of a pattern. Uh, so a realization of a pattern P denoted by this awkward symbol on density operators. So this basically the states in the input Hilbert space by sending the density operator to the sum over all possible branches, and those are the operations that are associated with the branching that we defined here. So this is sorry, I need to go over it. So this operation basically takes this and send this to this state.
Can I ask something else, Talay? Hello?
Yeah, I
Okay,
hear
so
you.
I thought it was frozen. So I think the AS supposed to be a linear map from L of HI to L of H. Oh, I think because you're also inserting downstairs there density operators, right? So I think you're thinking of it like a linear map from
Yeah,
L,
it's a linear map from.
but not from H, but from L of H, linear operators on H.
Oh, yeah, yeah,
Yeah. Okay, so because you should get something like a completely positive map or something, right?
yeah. This is the next proposition I will show. But before that, I will mention the kind of the one of the main theorems that I will discuss today. Uh, this is the theorem of the standard form. So basically, we are going to show that this is a channel. But before that, it will be very useful to have the standard form uh, discussion. So uh, this is the reordering of the comments in the pattern. So we can reorder comments in a pattern as preparation, entanglements, measurements and corrections. So we can always do that by conjugating the operations between them. But I will explain it. I will give a sketch proof of it because otherwise it will be a quite somewhat long discussion. So we already showed before that we have those relations with from the conjugation of measurement operators with Pauli's x and z, mi alpha s plus r and mi alpha t s z I r plus t mi alpha s. I'm using these arrows because those are not equalities, but since we are not concerned with the we defined the measurements as destructive ones, they will have the same realization. So it basically says that if a correction appears before the measurement, we can just merge it into a measurement. So if we have a measurement and correction, it will be just measurement. So we call it MC, rewrite rules. And we also have the following by they are just the Clifford identities for CZ gate. We have XIS, ZJS, AIJ, EIJ, XJS, IS, EIJ, ZIS, ZJS, EIJ, and lastly EIJ, ZJS. Oh, sorry, it should not. I I think it should be I, right? I just wrote it wrong. Okay, so we call it EC rewrite rules because entanglement and correction. So again, it basically says that if entanglement comes before corrections, you can move corrections out of the way. So they appear after the entanglement. And as we discussed, like we can, okay, I will write it more clearly. The first step after those rules, since preparation commute with all others, we can just move them to the right. It is because like we are doing nothing on those qubits before they prepared. So we can just move it at the beginning. This is one of the assumptions of the pattern, the constraints on the pattern. And also, for second, we can commute all corrections to the left by EC and MC. Because now, after the first one, we are in a situation that corrections appear in between of entanglement and measurement operations. But using these rules, we can just merge it into a measurement or just conjugate it, commute it with the entanglement operations to make them appear on the left. And lastly, commute all entanglement comments to the right after preparations. So before this part, we are in a situation that C's appear here, M or E, M and E's are mixed in here, and N's are here, the preparations and corrections. So one of our constraints is we are doing nothing after we measure on the qubit. So if Aij appears somewhere, there is no chance that Mi or Mj appears before it, because we cannot do this measurement, this operation after we measure ith or jth qubit. So basically, the amps and measurement and entanglement operations apply to distinct set of qubits when they are in between of those. So we can just commute all the entanglement to the right. Does that make sense? Uh, I can explain it a bit more if it seems confusing.
So are you moving, so you're moving the entanglements right before the end, right? So that's using some of these rewrite rules, I guess. That's
For the last part you say?
yeah.
No, like one of our, let's say we have Aij. We are in a case that Mij appears before uh, Mk alpha, right?
Oh, so IJK are different here, or
No,
they might
I chose it arbitrary for now, but
yeah.
since one of our assumptions in the pattern, so let me just go back to that. So this one says that no comment acts on an already measured qubit.
Hmm.
So
Okay.
it implies that Ij and K are distinct. So we can just reverse it because they operate on different qubits. So
Yeah.
this is not a formal proof because like I think we also need to show that it ends in a finite amount of time. Like it, because here, for example, we are creating more correction qubits when we conjugate it.
Hmm.
We can define the distance and show it formally that it will uh, converge in a finite amount of time. But I skipped that detail because I think it makes sense now, and I think everyone can agree that it will be the case. So, uh, so theorem. Let me state it again. The theorem says that we will have all ends, then the entanglements, then measurements, then the corrections. Since this is the like initial parts, you can see that the entanglement is different, is done only at the beginning. Then we are uh, going to start on operating on the prepared and entangled states to get to do the computation. So it separates the resource from the operation, and we have the entanglement resource ready after we do E and N. Okay, so now we can show the proposition that I mentioned before. This is for each pattern P, its realization is a channel. It takes from the input Hilbert space to output Hilbert space. So for proof, using the above theorem, we can write every branch as CS, pi s, and u, where CS is a unitary in the output Hilbert space. Those are the corrections. Pi s is a projection from HV to HO, and U is an isometry from HI to HV. So I guess those also need to be L ones. Sorry about that. Right?
No, you don't have the L's there. So because the projection is going to go between the Hilbert spaces, similarly isometry as well. But of course, normally you don't have them, but you can also treat the projection and the isometry as a linear map on the L's of those things. But I guess here you mean H1 or HI, HC, HO.
Okay, maybe I get confused because then what is wrong with this defining it like this, not in the H parts? Because
Yeah, that one is going to be acting on the L's because, for example, in downstairs,
the acts are by conjugation, you mean, right?
yeah. So
But
exactly. So yeah. So if you do by conjugation, for example, just take a projector or just take a unitary. I think this unitary would be the simplest case. So you can think of a unitary as a linear map from between the vector spaces or the Hilbert spaces, or you can think of it as a conjugation, and that would be like a channel.
yeah,
So
but here I was just trying to say that this is the map that maps the input state to the output one, as
yeah.
like it operates on the Hilbert spaces, not on the linear operators. Then we define this map as the channel by conjugation.
Oh, I see. So this is
Yeah.
your
I got confused in the other
cross
part.
operator. Yeah.
Okay, sorry about that. So
I think you're right. So AS is like a sequence of, yeah, I think it's a composition of linear maps. I think it looks right.
yeah.
If I can interject, this makes the AS basically the cross operators, right? I believe what you're
Yeah.
trying to prove now is that the trace preserving part using all those rewrite rules, because I've already shown that it's a completely positive map just by writing rho being mapped to summation over AS rho AS dagger. So
You are completely right. It's a
so
cross representation of the channel.
so it has to act on the Hilbert space, not the operators or the Hilbert space.
Yeah, you're right. So yes, they will turn out to be the cross representation of the channel, and we will have a channel. So I will just remove the confusion from here. Sorry. Okay. Then I will use a corollary. Let me say it. I will use the corollary 2.27 from Watrous. It basically says that since it is the cross representation of a map between linear operators, space of linear operators, if we show that the summing over S and AS, sorry, AS dagger AS is equal to the identity, then it's basically a channel. So let me remove this part and we will show it. So it is equal to just inserting these pi s dagger CS dagger, CS, pi s, and U. So since CS is defined as a unitary, this is the identity. So we can write it as summing over S, U dagger, pi S dagger, pi S U. And this is, since it's a projection operator, this is pi S. And also we can move the sum, since it's only dependent on S, inside to have this. And our since our measurements are complete, so we have this being equal to the identity, and it gives U dagger U. And since U is an isometry, we will have the identity. So it shows that the realization of a pattern is a channel. Okay. Is it clear? Now I will move on to the last bit of discussion, where I will show the universality of this computation. So I will just recall some facts from quantum circuits. First of one is any 1-qubit unitary can be written as the composition of the rotation operators as such. ZT. So recall, let's say. I'm taking this as a fact. Then let us define J alpha as 1 E I over alpha and minus E I over alpha, where alpha is a real number. So I will skip the computation, but this operation satisfies that Ry alpha equals AI alpha over 2. So basically you can write the rotation on y-axis as a combination of J operators that we defined above, and similarly for the Z as well. We have that sorry, a rotation about the Z-axis is equal to R alpha. So if we show that this operation is realizable by our computation, then we can realize all the single qubit unitaries. So I claim that the pattern, the following pattern, will realize the J alpha, and we're going to do the computations explicitly to demonstrate how patterns work. So x2 s1 m1 minus alpha, minus alpha a1 2 and 2. So so to do that, we are going to go step by step in the pattern procedure. So first, since we have one input qubit, just take psi equals alpha 0 beta 1 as an arbitrary state. Then after n, n2, it basically adds a plus state next to it because of how preparation works. So we can write it explicitly as 1 over square root of 2 alpha 0 0 beta, sorry, go like this, beta 1 0 and beta 1 1. So then we are going to apply the entanglement part. After we apply the A12, we will have A12 applied on the prepared qubits. So it works as such if the first qubit, it's symmetric, but you can take, if the first qubit is 1, it applies z to the second one. So this does nothing on this part. It also does nothing because I'm taking the control qubit as the first one, so those are 0. This is 1, but since 0 is a +1 eigenstate of z, it also does nothing on this part. But here it changed the signs because z on z, I can write it here, z1 is -1. So it just changed the sign. So after measurement, we have 2 branches. This is S1. Okay. Oh, sorry. I get confused. Then remember that we are measuring in the plus A alpha, but here we are taking the minus alpha here. So it will be the minus alpha state, which is the 1 over square root of 2, 0 plus E over minus I alpha 1, and the minus A alpha minus alpha is the same state with the minus sign in between. So if we collapse the first one, and we also, since we are concerned with the distracting measurements, we are also going to trace out the first part after the measurement. So we are going to be left with the 1 over 2. And since we are not normalizing it, there's no issue. So alpha plus E alpha beta 0 plus alpha minus E alpha beta 1. And the second part will be also similar. But here we are going to, okay, so sorry, this should be the, oh no, sorry. So the minuses just got reversed in here. But this difference will be solved with the correction. So it applies to the second qubit. So it is now the second qubit. And it basically changes, the applying x will change 0 and 1. So we are going to have this state at the end with certainty. And also we can go on and just do calculations here. 1 1 is minus I alpha, which is 1 over 2 alpha plus E alpha beta, alpha minus E alpha beta. So yeah, we can see that since those are same, this pattern that we defined here realizes the unitary operation J alpha. So there should be
is alpha overused?
Oh yeah. But yeah, but here alpha is not overused because this is actually the same alpha in the measurement. Like
But I think your psi,
it realizes the J alpha.
but your
So this alpha is this alpha.
but your psi also has an alpha. That's different alpha. Just in the next line.
Here?
No, just upstairs. The take psi is equal to alpha 0.
Oh, okay. Oh, yeah.
Yeah, I think
Yeah,
one of
okay, sorry about that. Yeah, I didn't think about it carefully. Sorry. Yeah, so which means that in our computation model, all single qubit unitaries are realizable. Also, from here, you can see that, like, no, not here, but sorry, there should be a square root of 2 sign. So from here, I think it is easy to say that J0 is the Hadamard gate, or like, so the pattern that if you put 0 here, it will also realize the Hadamard one. So moving on, I will also use another fact from the quantum circuits, which says that now the n unitary, so nu in C2 over tensor n, can be implemented by single qubit unitaries and CNAT, and also in O(n) square for n gates, but it's not important for us, this part. But this fact also translates to choosing CZ here, because for in the circuit we have the CNAT is equal to the CZ and just H's sides of it. So since we also include the all single qubit unitaries, just changing CNAT to CZ also satisfies this. So, but CZ is the AIJ operation that we defined, like entanglement operation. So we are basically done because we showed that all single qubit unitaries can be realized, and CZ is also realized. So we can realize all the unitaries in this framework. So that's about it. I plan to include in this talk, and also I guess the time worked very well.
Okay, yeah, very good. Any questions for Talay?